Welcome to day 21 of calculus. We're going to learn about the n-deriv function on your calculator, which will help us go deeper into our study of derivatives. First, let's remember some of what we know about derivatives, things that we can determine without a calculator. First, if we're given a graph, let's graph f prime. What could f prime look like? Well, what I've said many times is you first start by looking at where is the derivative equal to 0. It looks like it's going to be equal to 0 here, here, and here. Where's the function increasing? Well, this is f of x, so it's increasing from there to there, meaning the derivative has to be positive there and has to be positive there. So it means that we will have a derivative graph that falls down to there. It needs to be positive, and it also needs to be positive from here to here. Well, we know that the derivative needs to be negative there, and negative like this, getting more and more negative. So what's going to happen here? It's going to go down and then back up, and then it's going to go down like this. As a side note, we also started identifying kind of like steepest points. Like it looks like it's steepest right there, so that should be the lowest point right there. And then it just keeps on getting steeper down there. So that's one thing we could do with functions and derivatives. We also have this wonderful shortcut which tells us the derivative of polynomials quite nicely. So given this polynomial right here, find the equation of the tangent line. So the first thing I want you to write down is the point-slope form. And remember, you can stop once you've written the line in point-slope form. We're given one of them already. We're given x is equal to 2, so that's going to go right there. When it says use dy dx, that means find the derivative. This is just another way of saying y prime or f prime of x. It's all the same notation, means the same thing. So we need a point and a slope. Well, we know the x value is 2. So how do we get the y value? We do the function evaluated at 2, and that's just going to be 22. When you plug 2 into the original function, you end up with 22. So now we have our y1 value. Now we need the slope. Well, we need the derivative to find the slope, and we do not need to use the limit definition because it doesn't tell you to, and we have a polynomial. So we know that the derivative is going to be, you drop the 3 to the front, times 4, which is already there, x squared, because you drop the power by 1. Then it's going to be minus, you drop the power to the 2 times 3x plus 5. And then the 8, remember, is a constant, so it goes to 0. So we know our derivative is 12x squared minus 6x plus 5. And now when you plug in 2 into the derivative function right here, which we figured out, you'll end up with 41. So that just means our m value is 41. So we end up with y minus 22 equals 41 times x minus 2. Stop there. Unless you're forced to go further or forced to do something else with that, that is a totally fine answer. You can stop right there. Stop with point-slope form. So we could sketch a derivative. We could find a tangent line of a polynomial in a pretty straightforward manner, although the algebra is kind of annoying. That's what we can do by hand. Some of the things we can do by hand. So I could still ask you to find an equation of a tangent line, but let's do a function that's a little different. This is not a polynomial, so we can't use that shortcut. We do have the x value of 2, and we know it's going to be y minus y1 is equal to m times x. Well, we know it's going to be 2. We can find y1. y1 is going to happens when you plug in 2 into this. So it's going to be 2 times 2 plus 4 over 3 times 2 squared plus 2. So that's going to be 8 over 3 times 4 is 12, 14. So we know that y1 will be this. So we now know it's y minus 8 over 14 is equal to m times x minus 2. We are only part of the way there because we've just found the point part of this. We found the point. What we found was that when x was 2, y was 8 over 14. Now we need to find the slope. We can't use the shortcut, so we have to use the limit definition. Please still write down the limit definition whenever you use it. It minimizes the amount of small mistakes you can make over h. So this is our function right there. So what do we end up with? We end up with this big thing here. Remember, our a value is equal to 2. So we have a plus h. Our a plus h is right there and right there. All I've done was substitute that in for x in both of these cases. We also know that when you plug in 2, you get 8 over 14. So instead of f of 2, we could write 8 over 14. Now, it is possible to do this algebraically. You need to simplify the top, and then eventually you have to cancel that h because you can't plug in 0 right now. So you can do this algebraically. It takes a little while, and we'll do that in class. do it in groups, but definitely try it on your own. See how far you can get with the algebra. It is possible to do this algebraically. You have to be really careful with it though. Please be very, very, very careful with it. The answer does come out to be negative 17 over 49. So the reason I do this example is to show you that there are types of functions, not polynomials, that we can't use the shortcut on. We'll still have to use the limit definition, but it'd be nice to know if there's a way to use our calculator to find this number faster. So what about this magical n-deriv function on your calculator? The way you're going to use it is you're going to open up your calculator, and the first thing you're going to do is you're going to enter in the function into y1. So I've entered the original function, 2x plus 4 divided by 3x squared plus 2 as y1. Go to the main screen, and now if you go to math 8, so you can scroll down and just press 8, it's n-deriv. It might say n-deriv on your calculator, or it might look like this. Most likely it'll look like this. If you see n-deriv instead, we'll go over that in class. It's slightly different, but it's very similar. You're doing the derivative in terms of x, and it's asking what function are we going to do the derivative of? y1, and then that bar with the x equals, we're doing the derivative at 2. What this is doing is saying I want to do the derivative in terms of x of the first function, because that's where I put the function I'm taking the derivative of, at x equals 2. If I hit enter here, I get negative 0.3469. Let's see if that's equal to what I thought it would be. Negative 17 divided by 49. The decimals might be off a little tiny bit at the end, but it is the same. So you can plug the function in for y1, and then it's math 8. So again, math 8. You put x, you're doing the derivative in terms of x, and then you have vars, you have to select the function you're doing the derivative of, and then let's say you wanted to do the derivative at 3. That's the derivative at 3. I'm going to do second entry. I'm going to change this to, I wasn't sure if it was 2. Oh, let's check it. Oh, it's the same thing. But you can plug anything you want and it'll do this. Now, the advantage here was that this is the exact answer. On your calculator, it gets real close, and it can be exact, but it's doing a lot of estimation, so sometimes it's not going to be as exact. Either way, we've used our calculator to verify that that's the slope, and this is just the m value. So now we have y minus 8 over 14 equals negative 17 over 49 times x minus 2. That's the slope of the tangent line right there. So let's look at this next example. Suppose a person is walking on a straight east-west path and his distance in feet is given by the function d of t equals negative 5 sine 0.1 t squared minus 3t, where positive is east and negative is west. Evaluate and interpret. So first of all, notice it says radian mode. You should always be in radian mode on your calculator unless it says degrees. So to do that, when I quit out here, I'm going to go to mode. It's on radian right there, so that's great. So what I next have done is I've entered the function as y2, negative 5 sine 0.1 x squared in this case minus 3x. I'm going to quit out, and it's asking me to evaluate d of 5, so I'm going to do y2 of 5. I put the function as y2. So if I go back to the calculator here, I'm going to end up with, let's do this here, so second trace gets me, go back to quit, I'm going to do vars, y vars, enter, not y1, I entered it as y2, so vars, y vars, enter y2, and I'm going to do it at 5, and my calculator is freaking out a little bit. I'm going to delete that, and I'm going to delete that of 5, and then I'm going to do the same thing, second entry, and I think it says at 10, like this. It's freaking out a little bit. There we go. Okay, so what do each of these mean? Well, it means that at this time, what's the time in? At time 5. At time 5, it says, actually doesn't say what units t is in, but let's say this is in seconds. T is in seconds, and we know that distance is in feet right there. So after 5 seconds, the person is negative 0.331 away, and that's in feet. Feet away from starting position. But we know we could also say that as 0.331 feet to the west, because negative is west. And then this one would be after 10 seconds, the person is 4.56 feet to the east. Now, we can do the derivative quite easily now because we have this n-deriv function. You go back to your calculator, and on the main screen, we're going to pull up vars, go back to the main screen, hit math, and it's math 8. We're doing x, and remember, I plugged this in as y2. So I need to make sure I select y2, and I'm going to do it at, what did it ask for? 5 and 10. At 5 and at 10. At 5 and at 10. So I'm going to do it at 5 and hit enter. And then I'm going to do the same thing, but instead of 5, I'm going to change it to 10. Not 110, 10. Like this. There we go. So, what does that mean? Remember, these are rates, so this rate means that at 5 seconds, the person is now moving 9.977 feet per second to the east, and then at 10 seconds, the person is moving 2.04 feet per second to the east. So you can also graph these functions. So first, I'm going to turn off the y1. You could also clear it if you wanted, but you can turn it off by just unhighlighting the equal sign. So what I'm going to do here is I'm inside the graphing function for y3. I am going to do the same thing I did before, math 8 dx, not p. You see how I did p right there? Got to be careful, x. And you can still do vars here. So it's y vars. Remember, it's y2 for this one. So y2, so function, and then, we want to do y2. Now that it's y2, I'll go back to the calculator here. You want to put x as what you're evaluating it as. And then for this window, it said 0 to 10 and negative 15. You get there by clicking on window. So negative 10 to 10. Is it negative? So it's 0 to 10 and negative 15. So then you hit graph. So it's 0 to 10 and negative 15 to 15. So that was the function. And now look at the derivative right here. Here we go. It is graphing the derivative. Very cool. So this is what we came up with here. And I'll make this color here. This graph right here was the function itself. So that was the function f of x. And then the derivative is this one right here. It's right there. And how could we check that? Well, you can check it one way is looking at where is the red, where's the function derivative equal to 0? There, 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 and there. Well, the derivative should be 0 in each of those cases, and it definitely is. It's one way to check it. So you can graph the derivative really nicely now on your calculator. Again, how do you set it up? You set it up by setting up like this. I turned off the first function, and then you have d dx. What function are you doing the derivative of? y2. And then for this x part right here, you do it as x. If your calculator is showing you something other than d over dx, I will show you how to do that in class. What's now nice is that you can use your calculator just to fill in tables like this really, really quickly, because you can have your calculator manually compute not only d, in this case it was y2, I'm on the calculator as I set it up, and then you use the n-deriv function, the d over dx of y2 evaluated first at x equals 0, and then you could evaluate it at 1, 2, 3, 4, 5, and 6, and do it really, really quickly. Another way to do this would be to use your calculator for the table, and you get into table set, which is second window. We start at 0, and the delta is 1 because we're going from 0 to 1 to 2 to 3. The change is just 1 between the x values. So then you can go to second graph, which is the table. And remember, y1 I turned it off, so y2 is the function, and y3 is the derivative. And now look, it automatically computed all the derivatives for you. So you have all the numbers done out already if you use the table mode. This works because the distance between all these is the same. So you can then take this right here and just copy it down, and you end up with this right here. Remember, in this case, y2 was our function, and this was our f prime. So we have it at 0, 1, all the way up to 6, and here are the numbers. Nice.